Okay.
Oh, really?
But you don't have to start now.
Okay.
Just recording. Just
Oh. Okay. Okay. Hey, Sanju. So you must work with Phil, right?
Yeah.
Okay. Okay. Okay.
He's also here.
Yeah. Yeah. Did you guys travel together or?
Yeah, we did travel together, but flight got delayed and then we had to separate because I was in the standby in the morning.
Oh,
and,
I see. I see.
Everybody left for me and then they went to the different flight.
I see. I see. Okay. Yeah. He told me that he was challenged getting here, but yeah. Good you made it. Yeah, I got in at 3 a.m. This morning.
Like
Today, yeah. So, okay, off we go. Hey, so I just wanted to show a couple things on T3 that I wasn't managing to do in the throes of uploading all of those trials onto the sandbox. And hopefully this is just in the hope of getting everybody a little bit more comfortable using T3 to find data and download it. Certainly within my lab, I found that it makes it really easier to have grad student data from their grad studies organized. Okay, so here's the WheatCAP version of T3, and I just want to show a couple things on the wizard. I mentioned that on the back end, the wizard is using some tables that it assembles. These are called materialized views, but whatever, that it assembles to optimize the performance of this wizard. So when you upload a new trial, it has to refresh those tables, and that can take a while. So just for starters, yeah, the couple things I was trying to do before on the sandbox. Okay, so if you, in the WheatCAP instance, if you select trials in your first column here, it looks like there are 8,000 trials on the WheatCAP instance of T3. And so, what we were trying to do earlier was find this Texas Elite set from this year, and that Texas Elite set has this text in the name. So we can select that trial. So these are all of the trials that have TXE 2025 in the name. Now I've selected it. And so now I can, because I haven't uploaded a bunch of new files, trials onto T3, onto the WheatCAP instance, it's not reorganizing those. So I can go find out what the accessions are. And there they are. We know by now that there are 40 accessions, and so, whatever, it finds them. So I'm gonna select these accessions. Now I have 40 selected accessions. Well, so first of all, maybe before I select any, it's also relatively straightforward to go and download this data. Yeah, typically, so down here in the bottom part of the wizard, there's these download buttons, and we can download related trial phenotypes. Probably I don't know exactly how many phenotypes there are on this trial. It's a trial from this year, but I could go ahead and download them. Okay. So for me, for instance, as an advisor, if I have a student and I want to have a look at their data, it's very easy for me to find it when it's on T3. It's much more challenging if they've set up some kind of Google Drive or whatever. Okay, so let's say I want to know a little bit more about the accessions that are in this trial. I can select them, and I can make a list of these accessions. So I'm going to just call this. So lists can be of different types. You can have lists of trials, lists of traits, lists of accessions. I like to, if I'm making a list of accessions, I like to start it with just a little something that tells me what the type of the trial is. But anyway, so now I've made this list. T3 tells me, and I'm sorry it's in small font there, that it's added 40 items to a list. I am logged in. You can't really get onto WheatCAP without logging in. So there's this list of accessions. Lists are really handy tools, and we have a little bit of functionality to work with lists. So, for example, this is a little bit nonsensical because wheats in Texas are completely different from wheats at Cornell in Ithaca. But let's say I wanted to, if I wanted to look at whether there was any accessions in common across Texas and Cornell, I could click both of these lists and ask for an intersection. I'm guessing, I have to enter a new list name. I'm going to guess that it's going to be empty, okay? Empty list. And it asks me if I'm sure I want to make this new list, and I am. The selected lists don't have any items in common. New list not created. Okay, so if instead of having an empty list, I wanted to do a list that had the union of these two, again, it asks me if that's really what I want to do, and it is. So now there's 263 items. This comes from the fact that I had 223 from New York and 40 from Texas. Okay. Now I'm back to my wizard, and I'm just going to refresh the page so that I don't have this. And since I've just made a list, and I want to learn something more about these accessions that are in Texas elites this year. When you click on one of the columns of the search wizard, it gives you some data types, so accessions or locations or trials and so on. It also gives you a whole bunch of lists, and I'm afraid that we need to figure out a way to organize this a little bit, because all of these that I'm scrolling through now are public lists, and then finally I get down to my own lists, and here's this this list of accessions from Texas. So when I select it, the 40 accessions show up, right? It tells me that I've selected 40 out of 40 objects from the list, whatever. So what interests me here now is I can find out, okay, what other trials have these accessions been used in? So hopefully this has got to work. If I select trials, I find out that at least one of these accessions was present in 64 different trials, right? So that's kind of handy if all of a sudden I want to know, like, so for example, I won't go through this, but something that I could do is if I wanted to expand on this list with accessions that are probably somewhat related, you know that if two accessions have been assayed in the same trial, they're probably not completely different from each other, right? They're not a spring wheat and a winter wheat, for example, because it wouldn't make sense to assay those two in the same trial. So I could relatively easily select all of these 64 trials, get all of the accessions from these 64 trials, and all of those accessions I know would be somewhat related to these 40 accessions. Okay, I'm not going to do that, but I just want to show one other thing is these are the 64 trials in which any one of these 40 accessions has been looked at. I could also decide that I want a minimum number of 2 of these accessions in the one trial. And in that case, there are only 30 trials where at least 2 of these accessions have been assayed. So again, with this idea that that trials that assay the same accessions are probably assaying accessions that are similar, it would make sense to look at these trials. Okay, so for those of you who are in the know, the Argonne is the regional germplasm observation nursery. There's actually no yield data on this. But on the other hand, the Southern Regional Performance Nursery, there's yield data and so on. So if you have a set of, quick example of how to expand on a list. I can also find out if any of these have been genotyped. So I just refreshed, and now I'm going to go and find my list again. Okay, so there are 22 different genotyping projects that have genotyped at least one of these. It's a little bit trickier to find out if there are any genotyping projects that have all of them, or if they've all been genotyped one way or another. But you can see that if you want to find some genotype data, this would be a fair amount of data to sift through, but you could do it. and Tim is actually, so I'm showing you sort of the graphical user interface. A lot of this stuff you can do with BRAPI, the breeding application program interface, so that you can write a script that will sort through these kinds of things also. Right, so then the last thing I wanted to do was, let's say you're interested in longitudinal data, you want to calculate growth curves of different wheats growing. To calculate these growth curves, you want to find trials where there's been a minimum number of flights of that trial with drone data, okay? So this is a little bit more complicated, but you can use T3 to do this also. So now what I'm going to do is I'm going to select traits. Hopefully you can see this. There are 51,000 traits on T3. This is a little bit of an exaggeration. It comes from the fact that for all of these drone high throughput phenotyping traits, each trait is possibly measured on any one of 365 different days, and so each trait ends up being multiplied by 365. Also, it's multiplied by 2 on top of that, because as Jinhao was just showing, you can have the mean value for a plot, but you can also have the variation within the plot. So if I want to find trials that have been flown multiple times, I'm going to use drone. I need to find whether there are drone traits in those trials. And well, okay. So for starters, I guess I'm going to work with NDVI, and so it's sifting through all of the traits that say NDVI, and there's some that that I'm not interested in. Like I'm actually, who can tell me what GNDVI is? I'm not quite sure what it is. Okay, so, but it's something beyond NDVI. I know I'm not interested in it, so I'm just gonna make this a little bit more specific. Don't crash on me. Oh, I didn't write canopy correctly, so it didn't find anything. Okay, so now it's found canopy NDVI. There are different ways of measuring NDVI. I specifically want the unoccupied aerial system versions of NDVI. And so now now I've done this, and if I select all, it's finding 732 traits. That's because it's finding both the mean value trait and the variation trait. Excuse me, so I'm just gonna make this again a little bit more specific. Okay, so now I'm up to 366. Okay, so here, this is an average value. These are the specific days. Okay, so, I'm showing you something that it would be hard to replicate, but, whoops. All right, so now I finally have 365 NDVI traits that are possible. Okay, how am I going to use this to find trials where there were multiple flights? I'm going to use this little trick down here where I want to find trials that have, say, a minimum of 5 of these traits, right? Each one of these traits is indexed by a day. So if there are 5 of them, that means that the trial was flown 5 times. And I'm setting this as a minimum. And it's a little tricky. There's a percentage here versus a number. If you use percentage, then you'd want at least, say, 10% of the 365 traits to be present. That's not what we want. We want a minimum of 5 flights, and so now I'm going to look for trials where there are at least 5 flights, and there are 185 trials on T3 where you have NDVI measured 5 times over the course of the season. So if you're interested in trying to generate growth curves or NDVI curves, this is a lot of data that you can play with. Yeah. So that's what I wanted to show about T3. So, I really like this wizard function in terms of being able to find data. Are there questions about it or comments that you have, frustrations that you've had in using T3 that you want to bring up? Otherwise, I just wanted to. I was talking to some students earlier on about this prediction competition that we're going to have. The rules are going to be here, whatever. But just and I'd love it if anybody who has any thoughts about this, whether you think it's a good idea, bad idea, or what maybe you think it's a good idea, but you would need help of some sort being able to participate, come talk to me or send me an email or whatever. But, so very preliminarily, what we're going to do is contestants, and these can be teams. Haven't really decided what the maximum team size is. You submit a folder. R or Python already changed this, so if you want to do Python, that's great. But anyway, it would have a function. You'd give that function a wheat trial ID. It would return predictions for the genotyped entries of that trial in the CV0 or CV00 case. And I'm happy to tell you what that means at some other point if you don't know what it means. And then it would have to use data from T3 as training data, right? And so, we're still sort of sorting through exactly how we want to do this. We're going to finish sorting through that in about a month. And so final details of how this is going to work are going to be over here. And then I'm going to twist Tim's arm to give a talk at PAG in January, maybe. I don't know. Otherwise, I'll give it, but whatever. Where Tim is already developing some functionality to pull data from T3 that can help doing this kind of thing. And then everybody would have to submit that folder by March next year. And you could use any data that's available on T3, drone data, genotype data. Oh, and T3 typically links to weather stations, but you'd want to use data from weather stations to figure out. NASA Power is a standard one to figure out what kinds of environments were experienced by the trial that you're using in training, for example. Okay, so enviromics. And basically what we'd do is we would, to decide who wins, we'd pick 10 trials from T3 that were conducted recently, where we have yield data, we have the planting and harvest dates, and they have at least 50 entries that were genotyped. And we would run your script on those 10 trials. For each trial, there's 2 accuracies. There's a CV0 accuracy and the CV00 accuracy. We take the average of these 20 accuracies, and whoever has the highest average wins. And so then what we're going to do is we'll have a little meeting about this within WheatCAP. We will figure out how to publish it on G3. Actually, this kind of came to a head because Lauren McIntyre, who's the editor-in-chief of G3, Edward Akunov told her about it, and then she was like, this is interesting. So she asked me to formalize it, so we made that website with these preliminary rules. But they're on board to publish the results, and so anybody who participated, if you were on a team, you would be a co-author on this publication from WheatCAP. So like I said, I'm kind of excited. I think this would be a great proof of concept of the value of T3, so yeah, come talk to me if you have any questions or thoughts on how this could work. Cool. Thanks, everyone.
Okay. No, I'm very tired. You guys are very tired as well. I don't think I can do all this. I think I covered pretty much everything that I want to cover. And I'm going to end my training workshop by demonstrating that the plot boundary in the AI tool that we published, and just quickly demonstrate how it works. And let's call it a day, get some rest. I know that you guys have a presentation to make. You guys need some time to prepare. Well, let's.
Oh, sorry.
And I need to record my screen back again. Okay, so the GitHub repository where you can actually access that plot boundary extractor is at the bottom, pretty much the same as in a WheatCAP. It's at github.com, geospatial data science lab / plot-boundary - extractor. Just type that URL. And I don't think you guys need to follow through because there's a ton of packages to install. So I'm not going to I expect you guys to follow what I'm doing, but if you go to that the GitHub repository, this is going to be the the GitHub repo. We publish this module. This should be a public repo, so everybody should have an access to. And this is the actual the citation. So if you just Google this up in Google Scholar, google.com. Oops, where's the link? So this is a segmented animation model based on automated plot extraction. So you guys can download paper and read through it. And basically, I already have my environment set up on my laptop, so I'm not going to go through this, but create a virtual environment using Conda. I think that this one is tested with a Python 3.10, so I'm pretty sure it's going to work with a more latest version, but if you want to be on the safe side, you can just do this. Activate the environment and the pip install. This is a plot boundary extraction module. Is also one that we publish in a pip in a registry, so you can simply install this. And you also need a PyTorch to be installed because this is based on Torch. So pip install Torch, Torch Vision. If you don't have a GPU, if you have a CUDA GPU, NVIDIA, you have to install Torch Vision with this specific the NVIDIA CUDA library to it. After that one, you have to install segment entity model from Meta by doing this, and you have to download the pre-trained weight by just using this command line. So what I did here is that I just actually cloned this in a repository over here. And if I just give you the virtual environment, I created this in a plot boundary extractor environment created. I'm also activated. You can see it over here. And I'm going to do Jupyter Notebook. I'm going to start it from the current directory. And D2Spy plot extraction demo, Amarillo bit. I think this is example, the code that I got. I have again explanation of what to be installed and etc. Then I'm gonna be essentially running this in the cell one by one, like I was doing earlier, loading all the required module. So this one takes a little bit longer, because it may seem like there's nothing many, but this plot boundary extractor module is calling pulling a lot of other depending module over there. This is why it's taking a little bit longer. Some explanation about the structure. I'm connecting to this workspace, D2S, setting up the API key and the titler, and I'm finding a project that I want. So I'm going to be choosing which one that I'm going to use. You know what? Let me use something different. So we're going to be using the 2025 WheatCAP. So let's use the one that we created today to demonstrate how this works. So this last one is the one that I created for this workshop. So I'm going to choose that project. From here, I'm going to pick the one that is in April 28th that I got. So I'm going to choose that in a specific flight. I'm going to get all the product. And for this one to work, we need to use an ortho, because in a segment editing model requires the natural color images. So I need to pick up the ortho, which is, where is ortho? This is in index number 2. This is an ortho over here. So I need to choose ortho. Data product that I'm working on is the second one here. And I'm actually visualizing this layer. So this is the one that we were working on earlier, right? Okay. So what I need to do is I need to zoom in and I need to set the boundary. So remember, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is in upper left corner. So let me just pick and it really doesn't matter how it is, but I just need to, click that boundary here. Let me just move things around. I'm gonna just do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is corner, and 12 of this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So I need to make sure that I'm setting this one right. And going all the way here, this should be the ending point. And I'm creating this bounding box that contains that 12 by 10 in this way. After this, these are the information that I need to provide. What is a base layer? This is an ortho that we got, API key that we got, and where you want to clip this data to your computer. So I'm going to just do it. I'm going to just use a very simple test.tif. And number of rows is 10, number of columns is 12, and width and height 3.1 and 1.45. And the point per side. So this in the segmentation algorithm, they need to place the seed point. So how many points you want to start using as a seed point? Remember, we have a 10 by 12. So I'm going to just choose whatever the bigger number. So we just have to make sure that we have enough seed point distributed throughout the field. So I'm going to set this to 12. And RU threshold value, I'm going to leave this as some default value. These are some of the parameters to avoid any double countings and any noise to be included in, etc. And I'm going to leave everything as a default. And this is going to be what is going to be the GeoJSON file. So I'm going to say test output GeoJSON and the same checkpoint. This is actually the checkpoint that we downloaded from this in the last line over here. This is in a pre-trained weight value that you downloaded. So simply after these setting parameters, what I do is then, hey, do the plot boundary extraction and show the result on the map. Just run it. We're just clipping these images. They just resized it. And this one is in a Mac. The Mac GPU is not supported yet, I believe, in PyTorch. So I'm running this on the CPU. And initialize the seed point. They're just working on this plot boundary detection right now. So I think if this is GPU, probably by now I'll have the result, but I'm running this on a CPU. It'll take a bit longer. And you'll see how good of a job. I've never run this in algorithm to this in a specific flight. So I'm hoping that we are going to get some good result. Yeah, it's still running. You see the asterisk mark over there? Wow. Come on. It'll happen. Let me see, how am I doing on a CPU-wise? Give me a second. I'm just kind of curious. Oh, it is working hard. Oh. No. Now, I think they estimated orientation angle. It's a 25 degree. Something doesn't seem right. But we'll see how it comes out. Still working. I think I'm okay memory-wise. Oh. We're missing a lot of plot. I guess. Oh, they detected a missing plots. I think they are trying to detect those in a missing plot automatically. So I think multiple steps. Still running. No, I don't think I've never ran this on my laptop before.
How does it like managing the rotation angle? It is rotation of the whole rectangular polygon, or
I think more detail is included in the paper, but basically based on initial detection, we try to detect what is in a row and column direction. Based on this, we try to estimate what the rotation is going to be. Still working. And I think one of the benefit of this approach that we highlighted in the paper is that using that QGIS plugin, you're trying to match as much as possible, but you can only set fixed row spacing and column spacing. There are a lot of cases where your plot boundary is not placing exactly the center of the plot. A lot of times you're just getting close to the edge, and you all know that the phenotypic the calculation, you like to get close to the center much as possible. So we evaluated that centerness based on some metrics and compared that against whatever the manual delineation that we did. And we found that this gives us a lot more consistent, very well located at the center throughout that region.
Can we do single rows with this?
Single row? You mean as long as you have enough space in between, I don't see any reason why you cannot. I haven't tested it though. Maybe you can just try it out and see how it works. Wow, my laptop fans start to go crazy right now. Wow, this takes a lot longer than I expected. I should have run this on my the GPU workstation in my office, but I already kind of waited this long, so I'd let it finish. So you have to have the separation between plot for this to work. So if you have the largest plot where this plot is touching the neighboring one, I don't think this is going to work. So I think the timing is going to be critical. I know that Amarillo, you just plan almost continuous that you cut the alleyway. So if you're trying to apply this when people cut the alley, it's not going to work because you don't have a separation between the plot.
So in his program, they got their planter retrofitted this winter to where they're going to have like built-in alleyways.
Mm-hmm.
So they may be able to, but for single rows, we've never been able to.
Okay.
It just, because we irrigate ours, and so the plants just are all, there's no differentiation. I know some people can do it, but we can't.
There might be some kind of time during the growth season where it's early enough, you might see some separation between the row.
Yeah.
Because then if your images align very well, then you can use that, the plot boundary delineate from the earlier season can be overlaid to the later season data set, and you're sure that you're actually looking at the part of the plot.
By the time we get to the growth stage with the best predictive ability,
Mm-hmm.
it would be overgrown.
Okay.
It's only when the plants are juvenile that there's space in between. I don't know, somebody prove me wrong.
Yeah. But I mean, one advantage of this platform, like I just mentioned earlier, is that we are not giving you a tool that will solve all your problems. I'm just trying to give you enough tools so that you guys can tweak it so that it will work for your case. So we have all the code here, and if you understand the code, you can change in a way so that it may work for your specific case. Wow. I didn't expect this will take this long. Believe me, I tested it multiple times and it is quite amazing. Especially when you're running this on an NVIDIA GPU, it gets result very, very quickly.
Are you going to edit this part out of the video?
No.
I have some housekeeping things to mention, but I'll wait till we stop the recordings.
Yeah. Well, since we waited, let's give a few more minutes. And I think, I think what is happening is that whatever they're missing, they say that, hey, we should have 120, right? So we identify 76 or something that he believes that, hey, I'm missing 72. So they trying to place that, the seed one by one, run the same algorithm, go next and etc. So they may be doing, they have to do, iterate through those, 72 missing plot, one by one. That might be the reason why it's taking so long. Any questions? Really wish that this one I can see the result. You know what? Do I have? You see that this test.tip file has been clipped. So this is an actually file that we clipped from that D2S3 local machine, and we're using this one to run this segmentation analytic model. I don't want to kind of hold it too long. If you guys are interested in seeing the final outcome, you can just stay here longer. I think I'm going to stop here, my presentation. So thank you very much for your valuable time. I hope you guys enjoyed it. And before I end my presentation in a workshop, I'd like to give Shannon, Dr. Baker, a big round of applause for organizing this in a workshop. And I also like to thank Dr. Zhang and Dr. Wu serving as an TA in this session. And if you guys have any question, you have my email address. Please feel free to reach out. Thank you very much.